So we were in the middle of chapter 11 the last time, and we had done a couple of examples, talked about this linear value function geometry thing, but for now, I think I'm just going to go through in a little more detail the different types of errors and how to calculate them, and then the problems that can occur by using some of these alternative objective functions. And then, we'll see by the end an objective function, which seems to be like the correct thing to try to optimize for these problems. So yeah, sorry if it's sort of, I'm not going to go through like all the background because, we'd already, if you want to see more of that, you can look at the recordings of the previous two sessions for this. But, for starting in this section, there is this idea that there's this alternative objective that we could try to use instead of the value error. Remember, like the value error was introduced in chapter 9 here as this objective. And this is just looking at the difference between the approximate value and whatever the true value is, weighted across the states. And this is fine, but the problem is, we can't really estimate what the true value is unless we have, a Monte Carlo method, and we can't use Monte Carlo methods with continuing problems, or we can only do that with episodic problems. So that's kind of a limitation of this, which is what led to the consideration of these semi-gradient methods, which end up using the TD error or these update targets, which make use of the current approximation for the target instead of Monte Carlo sampling. And then this, is a semi-gradient method because there's this problem where now the thing we're sampling also depends on the parameters. So that's sort of the background idea. But there's other ways that we could use the bootstrap target. Like we sort of stumbled into the semi-gradient method by just trying to replace that, like using this sort of delta term, or in our sample of what the true value should be. But there's this alternative that we could look at, which is we could go back to one of the original things that we looked at in tabular methods, which was the Bellman error and the Bellman operator, which we had defined before. Now, like this equation here doesn't reference, I mean, it doesn't have to reference approximation necessarily, but like, let's say we have some function, some type of function approximation. I haven't even written here like any indication of what the parameters are, but this doesn't necessarily need to be like an approximation function. It could be any sort of value function or any current estimates of what the state values are. And then this is sort of new notation, but we're going to say that if we apply the Bellman operator to this thing, this current set of value approximations, that means that for a given state, we're going to map it to this new value. And this new value is just, what we had defined in part 1 of the book as the Bellman operator, where, we look forward to the transition state and we have, this target value is the reward we get on the transition plus the discounted value at the next state, based on whatever the current value estimates are. And then these sums just are sums over the probability of all those things happening. And then we can define, the Bellman error at whatever state this is, which is going to have this notation as the difference between, the Bellman operator applied to the state and the original approximate values that we had for it. And this should look familiar from part 1 of the book, because In part one, we had, derived the fact that there is this special value function for a policy for which, if we apply the Bellman operator to it at any state, we just end up with the same value. So we had said before that the true value function is a fixed point of the Bellman operator. And, it's a fixed point because if you are at this point of all the state values, then the Bellman operator doesn't change the point. So, it remains fixed under this operator. And it should also be clear then that this Bellman error that I've defined here, like this will be 0 for the true value function, right? We had also learned earlier, if you go back to this, this definition of the value error, if we have the true values, this is also 0. So fine, like in the tabular case, we already know that, we converge to the true values, and the true values have 0 Bellman error. So that's why, originally there was no problem with applying this fixed point operator, because we would always converge to the true values. But now that we're dealing with approximations, we should assume we're in a scenario where these v hats, whatever they are, we are unable to actually get 0 Bellman error because, right, like we can no longer just freely choose any values we want, right? The values are now constrained by how the approximation works and what the parameters are. So we have to then define a new objective using the Bellman error, but we're going to do the same sort of thing that was done with the value error, which is we can look at all the states and we can sum, these Bellman errors at each state. We'll, square them so that, this is what we did for the value error, so that, this is always a positive quantity. The minimum Bellman error is 0 now, if it's defined like this, summed across all the states. Y is, I'm sorry, Carrie, are you asking why the Bellman error is 0 for the true value function?
Yes, because earlier you stated that, so I was just wondering, why is that?
So this is all from part one of the book, and I'm not going to rederive it now, but this is just a property of the true value function that all of the state values are equal to this quantity. And this comes from the definition of what the value function is. But I mean, this is all from part one. If you look at the notes for that, a lot of part one deals with this and deriving these relationships, but it's just a property of the true value function that it is a fixed point of the Bellman operator.
Okay, thank you.
Yeah. But now with approximation, right, it will not be in general 0. So this is sort of an arbitrary choice again. We're going to define like what do we mean to minimize the Bellman error as much as we can, given that it can't be 0. And what we mean is we're going to sum over all the states the squared Bellman error and try to minimize that. If you write this out here, I'm just there's different versions of this expression. I'm just expanding it out here. This would be like fully expanded here. But, so this could have some solution. And in general, this solution will not necessarily match the solution that minimizes the value error or even the TD fixed point that we had seen before. And I have a new diagram I'm going to show, but I had shown last week this diagram, which was for a particular problem. And this diagram is sort of analogous to this linear value function diagram in the book, but this is just in 2 dimensions. And in this case, this blue line here represents the approximate value functions, whereas this whole plane represents all of the value functions. Like this happens to be a problem where there are 2 states. So the plane just represents, like this point, it just represents a value for both states. Like a single point, like here, the true value function is 4, 6. So that means state 1 has value 4 and state 2 has value 6. And the constraint is that in this case, we have just a single parameter to approximate two states. So this shows that the values we can approximate are constrained to this line. They're not this whole plane. So when we minimize the value error, we pick a point on the line that is closest to this point, right? So that's what we had found. Whereas this Bellman operator is totally different because the points that are projected with the Bellman operator are going to change as we move this, and minimizing the Bellman error is a point for which this projected point here is the closest to the line. And it is, in general, a different point. And actually, on this diagram, it will be a point over here. Here, if I move this, sorry. As I change this value, this is saying like this point is the approximation point that is defined by this weight value. And you can see as I move this, like farther away, the point of minimizing the value error is over here somewhere, because you can see this distance is getting smaller. But as I move more to the left, this point which represents where the Bellman projection takes you is actually getting smaller. And it's a totally different, optimization point than the one over here. So, but if you write it out, mathematically, this is the expression which is, I was showing before a diagram where there's only two states, but this is showing, you have to sum this over all the states, and then this quantity in the brackets here is the Bellman error for each state that is then, squared over this sum. So if we use this as an objective, we would have to find, here, if this v hat is dependent on some weight vector, we'd have to find the weight vector for which this entire expression is minimized. But yeah, the reason why this is sort of shown as this projection here is represented by this expression where for every state, we're going to take whatever the state was and project it into a new value, which is defined by this. And in general, like this could take on like any value, or like each state can have a distinct value after this projection is done. Okay, so are there any questions so far about these definitions? Right, or like what we are sort of, like what it would mean in this case, to minimize the mean square Bellman error. But I mean, yeah, there will be a specific example of this, which hopefully will make things more clear. But I just want to make sure first that the definitions are all make sense. Okay, so then this looks a little bit complicated. I mean, there's a lot of sums over probabilities here, because in order to compute this, we actually have to know or be able to sample somehow all of these different probabilities. But what's contained inside of here is something which looks familiar that we've been using a lot, which is the one-step TD error. And the one-step TD error, I mean, these are sort of capital letters in here because these represent a particular sample. So if we're at a particular time step, t, and we're in state S, then the TD error that we would observe for a transition is this, which is just the reward, the value at the transition state minus the value at the starting state, right? And this is just a single sample. So if there's like multiple transitions that could occur, this represents just a single observed transition. But one thing that's good about this, because we've been using it, is that we can always sample this from the environment, right? This error term. Whereas this, it might be unclear how we actually compute this. This is something that we could always, actually see from looking at some trajectory through states. So we could imagine using this as an objective also, where we would try to minimize the mean squared value of this. I mean, in that case, though, we would have to sum this over all of the observed transitions that would occur. And that's what's being shown here is if we imagine taking the TD error, but then our goal is that, as we observe transitions in the environment, we would like for the sum of all those transitions of the squared value of all of these TD errors to be minimized across all of the transitions that we observe. So this is different, in a sort of subtle way from the Bellman error. It's different because now, we're imagining we can just separate all the TD errors into like the ones we would observe, but we're going to square each of those where, each TD error is being squared individually. Whereas if you notice in this expression, we have a number of TD errors in here, which are being averaged over all the states. And we're only, squaring this quantity once we've computed, the entire expected TD error for a given state. Whereas in this case, we're saying, well, whatever TD error we end up with, all of the, a given state could have multiple TD errors because there could be multiple transition states if it's a stochastic environment. And in that case, we're going to try to minimize the sum across all of those individually. Now, if the environment is not stochastic, like if the probabilities here are always 1 for every transition, then actually these two errors are the same. So these errors are only differ when the environment is stochastic. And the difference there is that, the individual TD errors would be summed first in here and averaged before being squared. And here they're being treated individually. Now, we can look at this expected value, and we had previously used this importance sampling ratio, which I think it should be mentioned earlier in the chapter. But the importance sampling ratio is just this quantity, which we use if we're sampling values from a different distribution, that like in this case, B is a policy, which is what we are using to collect samples. But the policy we're interested in computing values for is pi. Then this importance sampling ratio is something where we can multiply it by the samples in order to correct for the expected value. That's what's being shown here is if we, in fact, instead collect samples under actions taken by the behavior policy, we can still maintain the same expected value if we multiply it by the importance sampling ratio. So that is what's being shown here. I think there still is this problem, like if you take this, so we want to minimize the sum over the visited states. If we imagine using this with sampling, then we would just be able to sample this quantity on each step because we would be visiting states under the behavior policy. And I think this should create like a different objective, like because we might still be getting the expected value of the TD error under the target policy, but the actual sum over the states is going to be different here. The book, I don't, it's possible I'm missing something about how this works in the book, and this is okay to do good. I don't think the importance sampling ratio corrects for this, right? Like, because this is still the expected value under the behavior policy. Even if this is the expected value under the target policy of the TD error. So I'm not sure if this is, I mean, I think what ends up getting computed here, this algorithm is computing this objective function, where we're summing this over the, mu, like where mu is for the behavior policy. But there's going to be an example of using this, or at least an analytic example. We'll see that actually we're going to analyze an example that shows that doing this is not actually a good idea, but it won't be clear why this is a bad idea until we get into the example. But, if we would like to minimize this quantity and we do the usual approach where we do stochastic gradient descent, so we're going to adjust the parameters on every step by a gradient of this, and each step, right, like if we have this importance sampling ratio times the TD error, which we can observe on each step, then we can see if we were to take the gradient of this, this is something that we can sample. Like to do SGD, we have to be able to collect samples. So here, this is just applying the chain rule to this, and the gradient of the TD error, the R term just goes away. And we end up with these two expressions here where we have the gradient of the approximation at the current state, and then the gradient with the approximation at the transition state. And like if you look at this method, this update rule should converge. It should cause the parameters to converge to the minimum TDE here. And you can see it actually looks very similar to the semi-gradient update rule that we previously had. And that was this update rule. This is what we use in all the semi-gradient TD methods, which this is adding the importance sampling ratio here. And these, if we do it in the on policy case, should converge to the TD fixed point. We had seen already that, if you're following a different behavior policy, the previous two sessions we did on this chapter were all about these cases where the semi-gradient algorithm here diverges in the off policy case, right? So apparently this is a way to avoid divergence, is there's this extra term here. And so we end up with this algorithm, and it looks different. And in order to understand why there's a problem with this algorithm, we're going to look at this first example here, this A-split example. So I think I might have mentioned this example briefly in the last time, but it's a very simple example, but it's worth, I think it makes it pretty understandable what's happening here. So the problem is just defined by this diagram here. So this is an episodic problem. There are three states, right, A, B, and C. We always start in state A, and then there's an equal probability of transitioning into state B or C with a reward of 0. And then both B and C will deterministically terminate with either a reward of 1 or a reward of 0. Okay, so the problem is very simple. it's very easy to see what the true values are in this problem. So, for these two states, B and C, the true values, because they end up in this terminal state, they're just the value of this reward here. So the true value of state B is 1. The true value of state C is 0. And then the value of state A just follows from that. It's just the average of the two, because there's no reward for the transition here. And it's just 1/2. Right? So is that clear to everyone for this problem? That, what the true values are?
So you're saying A is our initial state. We want our agent to go to B or go to C, right?
No, well, this is actually not, this is just a Markov reward process. So there's no actions here. This is just the agent will start in A and it will go to B or C with equal probability.
But aren't we teaching the
No,
agent?
there's no teaching here because this is just a matter of computing the state values. So there's no policy to learn here. This is just, I mean, like we're still at the point in the book where even to learn a policy, we still learn the value function first. The whole policy part comes from the value function. But all the theory I'm talking about now is just about finding the value function. Once you have the value function, you can then use it to find a policy if it's relevant. In this problem, the policy is not relevant because there's no actions here.
Okay.
So this is why it's a Markov reward process is just a system with states and transitions, whereas a Markov decision process is one where there would be multiple actions that you could take from each state. So you could imagine this is a problem where there's just one action in each state and you have to take that action. So it's a trivial problem in terms of the policy. But these are useful to estimate the state values because you're just isolating the value estimation part of it. You could also imagine that we have a bigger problem, but these arrows represent the actions that are being taken under the policy that we care about. So then the values that we're estimating here would be the values for that policy. But you can think of it either way. But like once you fix, like if you fix a deterministic policy, you turn the problem into a problem like this, where you just are trying to figure out what the values are for each state.
So for example, if we're teaching the agent to is it a cat or a dog? Is that what you're saying? Initially, we're just saying they could choose to look at the image and it's a dog, or it could look at the image and they could choose a cat. Is that correct?
It sounds like you're talking more about like a classification problem, which is not really the same sort of thing as these, Markov decision process problems. Yeah, sorry,
Then
I don't know.
oh, okay. Is the point
Yeah.
RL is basically your training, right? Your agent to be able to make the decision. So
Yeah, that's true in general, but there's a certain part of RL where we are just trying to approximate the values for a
okay.
fixed agent, which is what we're talking about here. So
Okay,
either the agent is fixed or here the system is fixed is this reward process where there's just a predefined set of things that happen. But yeah, this is all still in the case of value estimation. But anyway, for this problem though, the way it's set up, does it seem clear that these are what the true values should be? this, right? 1, 0, and then 1/2 for this stochastic splitting. Okay, so then the next step is to say, well, let's imagine we're going to approximate this, and here we're going to do something really trivial, which is imagine we have 3 parameters, W, A, B, and C, and in this case, we're not really doing approximation because, right, we can actually get an exact solution here, right? If the number of parameters equal the number of states, then we are just, in a tabular problem again. And we had already shown that, when we have these approximation methods, the ones we had previously looked at, if we have a tabular problem, then all the techniques we had looked at just find the exact solution, right? So, and that we would sort of expect that to be the case, like whatever approximation technique we're using, if in fact we have the ability to compute an exact solution, then our technique should find that solution. So here we have, these hats represent the approximate state values. So we have 3 approximate values, and they are just represented by these 3 parameters. Okay, and we already know what the solution is here, right? We just have WB is 1, WC is 0, and WA is 1/2. I mean, that would just be, we would just create the true values with the approximate values. Like technically, we do have to use the distribution of states because we always start in state A, and then it splits evenly. The percent of time we spend in state B and C is just 1/2 of state A. So this is just what the state distribution is. It's just half of the time is state A, and then a quarter of the time in each of the other states. So we already know what the exact solution is here. We can verify that the methods we had previously had recover that solution. So if we look back at semi-gradient TD0, right, this was one of the original methods we had from chapter 9. And, for this method, we have this form of the update. I think I already showed it, right? This is the update rule for semi-gradient TD. Here, like the gradient term is trivial because, yeah, each state, like all the gradients are just 1. So all we have to care about is the TD error term. And we have a TD error now that there's actually 4 of them. Right? There's 4 different TD errors, which represent the 4 different transitions that can happen in this problem. So 2 of the TD errors come from state A. Right? And the way you compute the TD error is we just take, 0 plus the value estimated B minus the starting point, and that repeats for all of these. So these 4 expressions here are just the 4 different TD errors that we would see. And each of these will actually occur with equal probability, right? Because you can see that there's 4 transitions here. All 4 of these transitions occur with equal probability if we were to collect samples from this problem. So we can look at these different TD errors, and these are the 4 different parameter updates that we would get if we were to, run this algorithm on this problem. And when this process converges, we would expect all the updates to be 0, or for all the updates to be 0 in expectation. So for parameter B, there's only one update we ever see. So this update has to produce 0 change. And that obviously occurs when WB is 1. And for parameter C, this only, right, is unchanged when WC is 0. So, we already know what WB and WC should be. And then for state A, we're going to observe each of these updates with equal probability. So we just need to make sure that after both of these occur, we expect there to be no change to WA. So if we sum up these 2 pieces, here we can see that, we're going to end up with, sorry, do I have this written out here? Yeah, so we can replace WB and WC also with what we know to be the optimal solution, right? So we have WB is 1. So we have 1 minus WA minus, and then WC is 0. We're just left with a single WA. And this is after both of the updates. And this implies that WA is 1/2. And that we already know is what the exact solution is, right? So under semi-gradient TD0, in the tabular case, this verifies that we do recover the exact solution, which we'd already proven that this should always recover the exact solution. So now we'll go back to this mean squared TD error that we had just defined, right? And now we're trying to minimize the expected value of the sum of all of the squared TD errors. And here we don't have to worry about the importance sampling ratio because, again, like there's no on or off policy here. We're just in a completely on policy case. And I already mentioned there were 4 of these TD errors, right? 2 for WA, and then 1. Oh, sorry, this should actually be WC here. Yeah, 2 for WA, 1 for WB, and 1 for WC. So here, what I've written out is just, there's 4 of these, so they're weighted by 1/4. The 1/4 doesn't really matter for the optimization. But each of these expressions is just the squared TD error for that transition. So you can write this out, you can expand out the powers like this. And then instead of, I'm not going to apply this whole update rule here because it's not really necessary. Instead, what I'm going to do is just find the point directly that minimizes this, right? So I can just solve this analytically by taking all of the different derivatives. So I can take the derivative of the TD error with respect to WA, WB, and WC. And I've already, expanded out these expressions, so it's pretty easy. You can, follow the algebra in the notes, but, you end up with these 3 equations, and then if you set each of these terms equal to 0, you end up with a system of equations. So there's 3 variables, and there's 3 unknowns. And you can start just, using your favorite technique of substituting terms. Here, I've turned the last expression, or the first expression, into one that just uses WA. And, you end up solving for WA first, and you end up with WA as 1/2. Okay, so that's good. I mean, that was the exact solution for WA we had expected already. And then you can see for WB, we have this expression in terms of WA, and you end up with WB is 3/4 and WC is 1/4. So we have the same value for WA, but apparently WB and WC, like this, we know the exact solution is that this is 1 and this is 0. But in fact, here we end up with 3/4 and 1/4. And this is in the tabular case. We have a separate parameter for each state. So if we use this objective function on this tabular problem, we end up with the wrong solution. And that is very concerning. I mean, it's actually just a reason not to use this objective at all, because we should always end up with the exact solution in a tabular problem. I mean, whether or not, it depends like how much justification you need for this being a bad idea. Like there's something wrong with writing this down as an objective where we're just treating each TD error separately. But clearly we end up with this problem, and it's probably, that alone is enough reason not to use this objective. The particular reason why these values are different is just, it's just a function of how this objective works, the fact that we're squaring, each of these terms, and weighting them equally. The book, I think if you read this section of the book, it does end up with the same answer, but this is just, if you want to see all the details of how to compute these values, it's here. But really, the point of this example is to show that minimizing the mean square TD error is a bad idea. So are there any questions about that?
Jason, I just put in the chat. So you said with tabular problem we should not do this, and what should we use then?
So the tabular techniques from part 1 will also, get the correct solution. I already showed that, right? This is showing if you apply semi-gradient TD0 on this, it works fine. So we already showed, at least in the on policy case, this works. But yeah, if you actually have a tabular problem, you don't have to use these approximation techniques. You can just solve it directly. The point of this is not really that you would use these techniques to solve a tabular problem. It's more that if you have an approximation where the exact solution exists, whatever technique you're using should find that exact solution. And this technique doesn't find the exact solution. So that it's just pointing out a flaw with this technique.
Okay.
But that's really the only point of this example. But the example is simple enough that you can see all the individual terms and how they work and compare it to the semi-gradient method. So we had looked, this was sort of introduced as a simpler version of the mean squared Bellman error, which, that was written out here. Now, if we have a tabular problem, like the one I just showed, I already explained here that if it is possible, to have an exact solution, the exact solution will have 0 Bellman error, right? So if we actually minimize the mean squared Bellman error, all of the Bellman errors will be 0. This will find the exact solution. So at least we know that this objective will not have the same problem as the TDE objective. Because in this problem, it would in fact find the exact solution, right? The problem with the minimum TDE error, as it's shown, it's explained here. The solution it finds here with the 3/4 and 1/4 is, what do they say? Is it 1/16th? Right? So this is the mean square TD error is 1/16th. And the mean square TD error for the exact solution is 1/8, neither of which are 0. So, if instead of this we computed the Bellman error, the exact solution would have 0 Bellman error, which is the minimum it can be. So, that would find the exact solution. So maybe it's more worthwhile to explore something that would minimize the Bellman error, because clearly this objective has some major problems. So if we go back to the Bellman error, we can hear I have it written out the way I wrote it at the end of the previous section where I expanded it out. And you can notice that, like, you can move this term into the brackets because, right, these are just probabilities. So when this sum is completed, you just end up with this full amount here on the outside. So you can move this into the brackets and then notice that this quantity in here with the sum over the policy is just the TD error, or the expected value of the TD error at a given state. We can write it out like this, right? But of course, we're squaring this after the sum term. So this entire expression in the brackets is just, right, the expected value under the policy of the TD error. And then if you look at it like this, final expression for the mean squared Bellman error looks very similar to the expression for the TD error, right? The only difference is this square occurring outside of the expected value instead of inside of the expected value. But we can, from this starting point, do the same thing we did with the TD error, which is take the gradient and see what we end up with. Here, when we apply the chain rule, now we have the expected value appearing twice here, and then we're left with this gradient term in here. And you can expand this out and you end up with a much more complicated expression than we had for the update under the TD error. And there's two different values here. You can verify from this expression that if the environment is deterministic, like I said before, you end up with the same thing as the update, as the TDE update here. Actually, it should be, well, yeah, no, because if the environment is deterministic, we can just remove some of these expected values. So, this is a bigger, more complicated expression. You can also see there's another problem with this, which is the definition of the Bellman error, right? Prior to squaring this, we have to take this expected, we have to know what this expected value is. And if we're just sampling these TD errors, right, like we have to sort of assign each of these TD errors to whatever state that we're sampling from. And there's this problem where when we're doing approximation, you could have an algorithm that creates a trajectory where you have different states. And the approximation function, like, it does not know the actual state you're in. What it knows is how the state is being represented by something like a feature vector. We had, I was showing here a case where we have different parameters for every state value, but in general, we have parameters that, like, they don't map one-to-one to states. We have some representation of the state, which is then used by the parameters. So let's say, like, the actual approximation function only knows limited information about the state. And then all these gradients that we compute, like, if we don't actually know what state we're in, all we know is this sampled value, then we can't use this expression because we have to actually be able to assign this TD error to a given state. Now, even though the approximation function doesn't know what state we're in, the learning algorithm we use could still use the state information somehow. But usually, that's not always going to be the case. Like we should, if we want the most flexibility possible, we should assume that we can do the learning just by sampling from the environment and looking at whatever the feature vector is of whatever state we're in. Now, if we have full information about the environment, like if we're in a given state, we actually can compute this expected value directly by like knowing what these probabilities are, then that's not a problem. But in the book, they derive this expression, and there's this comment here where, you know, right, we have to be able to collect samples of the value estimate at state S of t plus 1, right? And then here there's a gradient in terms of the value estimate at st plus 1. So we have S of t plus 1 appearing twice, and these are multiplied out. And the problem is that we can't just take a single sample of this and use it in both expressions, because that doesn't correctly compute whatever this expected value is. And it's just part of the rules of probability, but we're ending up with a product of expected values. And in order for this to be computed correctly, we need two independent samples of the next state, of some transition state. Now, either we need to know what the probabilities are of the transition state and just use that information, or we have to sample the transition. But if we sample the transition, we have to be able to do it twice. And we can't really sample the transition twice unless we know the starting state that we're in. Because like if we only know the feature vector of the starting state, that could be shared with other states. So we can't like reset the simulation to do that. So also, if all the transitions are deterministic, in which case, in that case, the TD error is the same as the Bellman error. And we said with this error, we could just take samples. We didn't have to worry about the environment. Like we didn't have to worry about knowing the exact state values. So if the environment is deterministic, it's fine. If the environment is not deterministic, which is the only case where this Bellman error is different, then we can't really use it unless we have additional information, like the ability to sample a state transition twice. But, let's say that we can do that anyway. Like, I mean, there's already some kind of problem with this where we can't just easily collect samples of this. So fine, but we could still imagine that if we have the required information about the environment, maybe we could do that. And, the point of this next example is to show that even if we could compute the Bellman error, it also has problems, or it doesn't lead to the solution that we might want. Now, this example is very similar to the previous example. The only difference is that instead of the problem being stochastic, like the previous problem, the problem is now deterministic. So state A is split up into two states, A1 and A2, each of which has a deterministic transition into B and C. But unlike the previous example, we're not going to treat this as a tabular problem. We're going to treat it as a problem where there is some parameter which shares, like, we have the same approximation for state A1 and A2. So from the perspective of that approximation function, this example is the same as the A-split example, right? Like in this example, the problem itself is stochastic and there's only 3 states. In this example, like the true problem has 4 states, but if the approximation function is just grouping these 2 states together, then it just looks like it's the other problem. So like all the data from this problem should look exactly the same, under this approximation. But here I'm showing, this problem, again, the exact solution is also trivial, just like the first one, where we have state B and C each have a value of 1 and 0. And there's two A values, which just share the same as the B and C values. A1 is 1, A2 is 0. And if you average these together, you get 1/2, which is the solution for the first problem. So we're separating out the 1/2 value into these two components of 1 and 0. But for the approximation function, we're saying there's a weight, just like we're using the same set of parameters as we had for the first example, WA, B, and C, where now both the approximation for A1 and A2 is shared by WA. And there's an equal amount of time spent in all four states. So the amount of time spent in the A state, which is like the approximate A state, if we don't know which of the two we're in, is 1/2 again, just like with the first example. But the true probabilities of the state distribution are 1/4 for each state. It's just the 1/2 is now split between the two. So does this so far make sense to everyone?
So what you're saying is the first example is we already defined the states, right? Like A can only go to B or go to C. But here, the second example is you're saying it's all about probability. It could be either or. Is that correct?
In the first example, state A has a stochastic transition to B or C with 1/2 probability. In this one, we are splitting that up into two deterministic transitions. So now the whole problem is deterministic with 4 different states. But if this is hidden from you, like you can't see you're in A1 or A2, you can only see you're in A, which is what the approximation function, right, can't distinguish A1 and A2. So if you can't distinguish them, yeah, it looks just like the previous problem, where if you're in one of these, if you can't tell which one you're in, half of the time you'll be in this one and do this. The other half of the time you'll be in this one and do this.
Okay, but then where are the 4 states coming in then? Because you're saying we already separated the A1
Yeah, yeah.
that will only go to B and A2 will only go to C, right?
Yep. And they're, yeah, these are the 4 states, right? A1, B, A2, C. But if we're approximating the values, both A1 and A2 will be approximated by the same value, right? WA. That's where they're only being combined from the perspective of the approximation function. In reality, there are 2 distinct states. If we could see all the states individually, there would be like, we would know if we were in A1, we would only go to B, never C. But the point of this example is more realistic for whenever we do approximation, this is the scenario we're in, where we have a problem with many states, but the way that we're representing them groups certain states together in some fashion. In this case, it's very simple. There's just 2 of the states are being grouped together. And they're sharing this value. So, this problem, I already said this is the exact solution. Now the value error, the minimum value error solution will not have 0 value error because it's no longer a tabular problem. We can write out, the value error because we actually know the true values. So these are just four terms here. Each of the four terms is just the difference between the approximate value and the true value. So we have, WA being compared to 1 or 0, and then WB being compared to 1, WC being compared to 0. We can write this out. We can then compute the minimizing, or the gradient of this, and see what minimizes it. And we end up with, not too surprisingly, that WB and WC each have the exact value, right, of 1 and 0, because we can represent their values exactly. WA, we're forced to choose a value, and it's not too surprising that the value that is best to choose is the one that is in the middle, right? This true value, right? This true value is 1, this true value is 0. The best value to choose to share between them is just 1/2, right? But you can see that from doing this minimization. So hopefully that's pretty obvious. And this is also the same as the exact solution for the previous problem. The difference now is that in the previous problem, the value error was 0. Now the value error is 1/8 for this, because while these two have the exact solution, this 1/2 is exactly 1/2 off of the true value for each state. So if we average that all together, yeah, 1/4. I think this is correct. Yeah, but the point is that the value error is not 0, right? Because we don't have the exact solution anymore. In particular, the solution for A1 and A2 cannot be exact anymore. But the best value for WA is 1/2. Okay, now we can look at how we defined the mean squared Bellman error and see, what if we try to minimize the Bellman error? Well, this is the expression for it. We can sum over the states. We have to know what the expected TD error is for each state. Luckily, in this case, like the TD error, like the problem is actually a deterministic problem. If we can distinguish all the states. So this is showing all the 4 different TD errors squared. But, I'm just writing this down from the definition of the mean squared Bellman error. But if you look at the previous problem we did, right, or I'll go back to this example. And I already wrote down, how do we find this minimum TDE solution? And I wrote this out, all the different TD errors. And you can see it's the exact same expression, right? Because here I'm writing out all the different TD errors. In this example, because the states are now separated, the individual TD errors here are now mimic what we had before for the TDE. So I already solved this, right? Like this was already the expression written out. This is already solved, and we already know what the solution is for the previous example, and it was this 1/2, 3/4, 1/4. So now, value WA has the correct value, but WB and C now have those same non-exact values that we found before when we tried to apply the mean squared TD error. So even if we have this full information about the problem, like we use this full knowledge of the states to write down the minimizing mean squared Bellman error, and we again end up with a solution which is clearly, far away from what it should be, or like it's not. I mean, in this case, we can't have an exact solution, but we know at the very least. I mean, we can represent the value of state B and C with their exact values. So like we would never want some sort of algorithm that just like needlessly produces the wrong values for 2 of the states. And again, like the reason why these values are different from 1 and 0 is because it helps lower the Bellman error for state A by doing that. Even though, state A is already as good as it can be, right? Like we can't do any better than setting this WA to 1/2 because it's right exactly in the middle of the two values it represents that are both equally likely to occur. So you could see the flaw of even trying to use this Bellman error is that we're sort of, we're sacrificing the value of two states to try to lower this error, even though the parameter, which is the only parameter that determines the value of this state, is already at the best possible value. So, we end up needlessly sacrificing the value of state B and C. Now, if you look at the TD fixed point of this, which is what you would get with the semi-gradient method, which write these out, right? These updates, if you write them out, again, are the same as what we had for the previous example. And those reproduced the solution that minimizes the value error, which is the 1/2, 1, and 0. So, just like this example, which is just a slight modification of the other one, is an example where all the problems we previously thought were with the mean squared TD error come up again with the mean squared Bellman error. And this is actually a case where we'd actually use this technique because we need to, approximate the states somehow. So this is one indication of like the Bellman error might not be converging to something that's actually desirable. There's that other problem I mentioned, which is that in order to apply this, we have to actually know what these expected values are, or we need to be able to sample the transition state multiple times. Like that, there's some extra information we need to know about the environment in order to use the Bellman error. But this is also an example that comes up later where, like, if you do the approximation where you group these states together, the data from both of these looks exactly the same. Like we're in like some representation of state A, and we go to B half the time, C half the time. It's the same thing here. But if we try to minimize the Bellman error on this problem, we end up with the exact solution because it's a tabular problem. And if we try to minimize it on this problem, we end up with a different solution with these, values of 3/4 and 1/4. So we end up with a totally different solution just from the underlying nature of the problem, even though from the perspective of looking at the state transitions and how the approximation function is going to group states together, like the problems look exactly the same. Like you only notice the difference in the Bellman error by being able to, peek into what is hidden, like what is obscured by the approximation function. But that is sort of a segue into this concept of like, in addition to the Bellman error, not converging to what appears to be the correct values, it's also not, it's not learnable it's not learnable from data, which is how this chapter is going to define learnability. Is like, if we have a problem, we collect samples from it, we can only look at the state representation, not the states. We would want to pick techniques where the same data produces the same optimal solution. And that is not the case for the Bellman error. Even though they add more examples here in this section, that's already the case for these two examples. Like these two examples will have the same, apparent data, and yet the optimal solution will appear different. Yeah, the TD error is big. Yeah, and you could calculate the Bellman error based on samples, but only if we're allowed to sample in this manner where we could collect multiple samples from a given state, from a given state transition. So we'd have to sort of reset it. But if you look at the value error, like it's true that you end up with two different Bellman errors, but right, I already show with these two examples how, in this case, this solution, the value error is not zero, right? Whereas in this one, because we have a tabular solution, the value error at the best parameters is zero. So clearly, like we also have two different quantities for the value error. However, the solution was the same for both that minimize the value error. And there's this theoretical discussion of this, which explains why, even though the value error will change with the problem, even if the data is the same, the actual solution will not change. And the reason for that is proven in this exercise, which what it ends up proving is that we already had this expression for the value error, right? Where we are comparing the true values with the approximate values at all the states. Now, we don't actually have access to the true values for most problems. I mean, if we did, we would be done anyway. So consider instead this expression, which is called the mean squared return error. Now, the difference between this and the value error is that we are replacing the true value with G here, which is a sample of the true value. Like this is what we would collect with Monte Carlo sampling. Now, the claim is that now this is always possible to sample. Like we could always, with just data alone, compute this. Because like if we're in a state, like whatever it is, we have the approximation for that state. And we have G for that state. And if we don't actually know what state we're in or the states are being grouped together, it doesn't matter because all of the states that end up sharing the same representation and will share the same approximation value, we are going to end up computing, the expected value of G, like it's all going to be averaged together. So it doesn't matter that we don't know exactly what state we're in. We can still, just with sampling, like all of the different states that share the same approximation are going to get grouped and averaged together when we compute this. Now, this is only depends on the data. And the claim is that this error term is just the value error that we were trying to optimize before, plus this term. And this term is just the variance of the discounted value. So if the problem is deterministic, like if we always end up, like if you take a state and you try to compute the discounted value of that state, if it's always the same, then this is just zero and they're exactly equal. This term is not zero when you have a combination of a policy and an environment where there's some distribution of values that you could end up with, of state values. So, but notice that this expression doesn't depend at all on the parameters, W. So if we were to try to do an algorithm that minimized this error, and so if you take the gradient of this, it's the same as the gradient with respect to the value error. So any set of problems where these sampled values appear to be the same will all share the same optimal solution. So it doesn't matter that the value error itself could be different between, like, this variance term could change depending on the problem, but any change in this term will not affect the parameters that are the optimal solution to this. So, I mean, this relationship is key to showing that any sort of objective that either directly minimizes the value error or tries to minimize the value error will end up not being affected by anything that doesn't affect the data distribution. Whereas something like the Bellman error actually had different solutions, even if the data distribution is the same. But this exercise 11.4 is to prove this relationship. The proof, the key to this proof is using a couple of these relationships from previous chapters. So like this is the thing we're trying to prove, that this, or what is this called again? The mean squared return error, that minimizing the mean squared return error is the same as minimizing the value error. But if you start out with the definition of the mean squared return error, which is here, and then you add and subtract the true value, then what you can end up doing, right? So like here, I'm just adding 0 inside of the parentheses here, right? Because I'm just adding and subtracting the same thing. And then you can regroup the terms. So here there's like 4 terms. So I'm grouping the G with the V, the true value function. And then I'm grouping the value function approximation also with the true value function. And then, if you multiply this out, right, this is the cross term here. These are both of the terms you get from squaring each of these expressions. And, sorry, this is a little cut off. Now, one of these terms ends up being, so one of these terms ends up being the same as the value error, right? Like the reason why I group them in this way is because the value error is just the difference between the approximation and the true value. And we know that the true value function is just the expected value of G, right? So G. And then, so this term here, this first term of the squared values, this is already the thing that we care about, right? This is the variance term between the actual return and the true value function. This expression in here, believe, oh yeah, sorry. So this already has the true value function. So you can see here just from the definition of the value error, right? We already have this term here. This is equivalent to the value error. This is the variance term. And then the only thing remaining to show is that this cross term just cancels out to 0, which in fact it does. The way it cancels out to 0 is that, right, you end up replacing this expected value of G with V pi. And then you see that, this term, you get this V pi squared, which cancels out. These terms cancel out. But I mean, there is some algebra here, but if you follow the tip in the exercise, which is just adding and subtracting this quantity, and you expand all the terms, you end up showing this. But, the whole purpose of this proof and this statement is that this thing that we can actually sample, that the reason why this wasn't mentioned before is because, minimizing this is the same as minimizing the value error. Like there's no difference, even though the values themselves will be different, the solution won't be different. And that's the important part. Now, there is this other counterexample here. Is kind of like this counterexample is another example which shows that it's another example where we group two states together. So if you look at these two problems, these are different because they're continuing problems. They are not episodic problems, but this, and they're all stochastic, actually, like both the left and right are stochastic problems. If you imagine grouping these two states together, when you're approximating, then you can see that like from this state, there's a transition with a reward of 1. From this state, there's 2 transitions, but they both share a reward of -1. And it ends up being equivalent. Like the left and right problems appear equivalent in terms of the data they would produce if you group these 2 states together, which is what will occur under the approximation. And just like the previous set of examples, the solution that minimizes the Bellman error in that case is going to be different for both solutions, whereas the solution that minimizes the other error is like the value error, for example, will not change depending on that. But to actually write out, like again, in the book, they don't write out like the full solution to both of these expressions, but I am just going to try to quickly go through it here because I do have sort of another diagram that shows how the different values work for this example. But if you try to compute the true values, you can do that just like we would in part 1 of the book by using the Bellman equations here. Because this is a continuing problem instead of an episodic problem, we have to write out the system of equations for the different values, right? So all the values depend on each other, but just, this is like exactly the kind of problem that would have been solved in part 1, where you write out, the value of state A is just equal to the reward of this transition plus the discount rate times the value of state B. And then the value of state B, we write out the same, Bellman equation for it, but with the probability split in half of these 2 transitions. But either way, you end up with an equation. Sorry, so this is an equation for the value of state B. You have 2 equations, 2 unknowns. You can solve for the value of state B, and you end up with this expression here, where the value of state B is equal to the value of state B times this expression. Of course, gamma, like the discount rate, we haven't said what it is. It could be anything from 0 to 1. I mean, it can't be 1 because it's a continuing problem. But it turns out that for this problem, the discount rate doesn't affect the values. Just the value of state B is 0, and the value of state A is also 0. So this problem is sort of contrived so all the values are 0, conveniently. Now, for the right problem, we have 3 states. So there's going to be 3 equations, 3 unknowns. And if you solve it, you end up with pretty simple values, but you end up with state A has a value of 0, state B has a value of 1, and state B prime has a value of -1. So if you imagine grouping state B and B prime together, they also occur with a 1/3, like all 3 of these states in this problem occur with 1/3 probability. So you would want to select a value in the middle of the 2, which would again be 0, right? In the middle of 1 and -1. And if you have the solution where you have 0, 0, that has 0 value error for this problem. For this problem, you end up with the same solution, which is important, right? The whole point of this example is if you group these states together, the data looks the same between the 2. So you would hope the solution that minimizes whatever we're talking about, like the value error, is also the same between the 2 examples. Now, that's what I'm writing out here, is that this is for the second problem where the value approximation of B and B prime both share the same parameter value of W2. Yeah, but if you actually write out the whole thing and try to minimize the value error here, for the left problem, we just end up with a tabular problem again. The solution is exact. The right problem, is not tabular, but if you do the algebra computing this gradient, you end up with the exact same solution. W1 and W2 are both 0. However, the value error, right, is not 0. It is it 2, 3? I'm not sure if I forgot to square something here, but the point is like the value error in this case, again, it's not 0. So we have two different value errors, but they share the same optimal solution where all the weights are 0. Now, we can try to do the same thing where we try to minimize the Bellman error, which is also what we did in that the pre-split example. And here, the Bellman error, right, we have to have the expected value of the TD error. Now, in the case of the first problem, we just have these two states. Now, the way this is set up, this state is visited 2/3 of the time. This state is visited 1/3 of the time, which is why it's equivalent when we group these two. These each have a 1/3 visit count. So from the grouped perspective, these problems look equivalent. And this is the expression for the Bellman error for the first problem. Now, like, and this is again weighted by the distribution of visited states. And here again, the TD error for state B is, right, each of these occur with 1/2 probability. So here they're being summed, and the squaring doesn't occur until after the expected value is computed. So if you look at this, we already know this is a tabular problem. So the minimizing value for the Bellman error, like it will have 0 Bellman error. And we can see that, right, each term in this sum is just either multiplied by W1 or W2. So if we set W1 and W2 both equal to 0, we end up setting the Bellman error to 0. Okay, so that's not too surprising. That is just the exact solution. Now, if we look at the second problem here, I mean, here, if you want, like, you can actually do it with the gradients too, but it's not necessary. Now, the right problem for the Bellman error, here there's 3 different terms. These are for the 3 different states. And each state, like even though state A has 2 different transitions, they occur with equal probability. They each have a 0 here. So here what I'm writing out, and also the transition state here, even though it's going to 2 different states, they both share the same approximation value, right, of W2. And that's also true of this one. Like, even though it ends up transitioning to 2 different states, the 2 different states share the same approximation value. So that's why there's no 1/2 in here, because I'm just combining the 2 transitions together. They both are the same value. But you have these 3 terms here, and you can compute the values of W and W2 that minimize the mean squared Bellman error. Here you actually do have to compute the gradients because the value is not going to be 0. And if you do that, you end up with this expression for W2, for W2. Well, okay. You end up with, I'm sorry, I think this, sorry, I think this needs to be removed here. I think you end up with this expression for W2, which is some complicated function of gamma, and then an expression for W1 in terms of W2. But you can see the values here. If you set gamma equal, if you take the limit as gamma goes to 1, you end up with this limiting solution where W1 is 0 and W2 is -1, which is, of course, right, different from what we know is the best value error solution. where both values are 0. We end up with a correct value for W2, but again, like W1 is quite far from 0. All right, and for the first problem. So just like in the previous pair of examples, we have two problems where the data looks the same with respect to the state representation, considering we're grouping the states, but you end up with a completely different answer for the Bellman error. Now, if you take, you can use this example to sort of recreate. I already showed a version of this plot in 2 dimensions, but you can use this example to actually do this like 3-dimensional plot here. You can kind of see what's happening. What's being shown here, again, the reason why this is 3-dimensional now, it's looking at this problem, the right side one, right, where there's 3 states. So this space, this 3-dimensional space, is the space of all of the value functions for A, B, and B prime. And then the plane here is the plane of all the possible approximation functions, where we can pick whatever value we want of state A, but then B and B prime, or again, like V and C here, I'm just calling this C, share the same value. And that's what this plane is representing, is it's the plane of points in the 3-dimensional space where the states 2 and 3 share the same value. So you can sort of see, I mean, in this diagram, they just show the 2 parameters here as like the 2 axes, which is these 2 lines here, these axes. But it doesn't show like the larger embedding space. I mean, it's just implied by this diagram. This diagram is showing, you know, both like the full embedding space of A, B, C. So like this point up here, yeah, wait, if I move here, I'll move this point so it becomes distinct. So this red point here, this is the true value function, where the values are 0, 1, and -1, right, which we had already solved for. And then you know that the solution that minimizes the value error is the solution where W1 and W2 are both 0. And if you see, like, here I'm showing this line, this 3-dimensional line here, is showing what the value error is. Like, it's the distance from the plane, the point on the plane, to the true value function. And you can see that at the origin, at 0, 0, right, that is the minimum distance. And it's also perpendicular to this point. But it's perpendicular to the plane here, right? It's not perpendicular to this axis, right? Because this whole space, you can see, is rotated so that this plane is sort of flat. But, you know, if you were to rotate this, like, so that one of these other things, like, you can see how this plane is oriented, right? Like any plane where the 2 state values share the same value, it's going to be some kind of plane like this, which is like sort of a y equals x line extended into the plane. But the other thing being shown on this diagram is this orange point. This orange point is the Bellman operator being applied to the approximation function. And here gamma is here. If I set gamma to 1, I already showed that the minimizing solution at that point is W1. Sorry, it's on this chart here. W1 is -0.5, W2 is 0. So instead of being at the origin, and just geometrically what's happening here is at this point of the origin, the value error is minimized. But as I move W1 over to this point, it's hard to see exactly, but you can see how this orange dot is getting closer to the plane, and the distance is the shortest at W is 0.5. You kind of see here exactly where this orange point is. At the minimum value error solution, this orange point moves up to here, but the distance is actually shorter at this point, which is the minimum value error point. Or also, that's what's being computed analytically here. But on this diagram, it's showing how, right, this point in the middle here at the origin is the solution we would like to get, which also matches the solution we would get, the exact solution for this problem. And then this point over here is the solution we end up getting when we try to minimize the mean squared Bellman error on this problem. And this plane is always defined by how the states are represented. Like this plane is sort of defining the fact that these two states share the same value. You could pick like these feature vectors for the states, like there's two parameters. The feature vectors could be anything. Like in this case, the feature vectors are like 1, 0, 0, 1, 0, 1, where these two share. But you could have three entirely different feature vectors, but either way, they would end up defining a plane in this space. It's just the plane might not be the same as this plane, but you end up with the same sort of setup where you have this slice through the space of all value functions that represent the ones, the only ones that you can represent with the approximation function. But this is sort of a summary of the problem with the Bellman error, which is what these previous two pairs of examples showed, which is you can have two different problems. They produce the same data distribution with respect to the state, like the state representation. And then not only do you get two different values of the Bellman error, but you end up with two different solutions that don't match. And in contrast to that, if you look at, well, right, this we can only compute with Monte Carlo sampling, but this solution, like even though the two different problems could have a different value error, a true value error, they will always share the same, whatever, I keep forgetting the term for this they use, or the residual, they will share the same residual error, which means that they will produce, the same solution. And then, the final thing, which is proposed in the chapter to compute this projected Bellman error, which it turns out this projected Bellman error, minimizing this is like the same as finding the TD fixed point. And this also only depends on the data distribution and will produce the same solution. This one we looked at before, this also only depends on the data distribution, but we saw that it converged to values that were incorrect, even for the tabular problem. So again, like the Monte Carlo objective is nice, and we have a lot of guarantees for it, but we can't use the Monte Carlo objective for problems like this, because these problems, they're continuing problems. They're not episodic. So we sort of have to consider bootstrapping objectives at some point, like we're forced into it. And we already know that this one is not good. And these we can't even use unless we have more information, and they also don't produce the solution we want in certain cases. So, we're left with this, which I mentioned in one of the earlier sessions, but this is the projected Bellman error. And what this is if this point represents the Bellman operator applied, if we project this down to the plane, the closest point in the plane that represents it, the projected Bellman error is the distance between that projected point and this point. And actually, if you look at this problem, if you move the approximation back to the origin, you can see the Bellman point moving. At the origin, the Bellman operator points straight up from the plane, which happens, this isn't always true, but for this problem, the point where the projected Bellman error is 0 also matches the value error solution. We know that that's not, in general, the TD fixed point, like it's shown in this diagram. The TD fixed point is the point of the projected Bellman error being 0. But it's not always the same as this point, which minimizes the value error. In this problem, it is the same point. But it's always the point where the projection takes you, perpendicular to this plane of approximation. And the final algorithm in this chapter, this gradient TD algorithm, is an algorithm which directly minimizes the projected Bellman error, which is the way that we're going to create an off-policy method, which, at least in the linear case, has these convergence guarantees that we didn't have for the semi-gradient method. Now, like the derivation, I mean, conceptually, the nice thing about this is that, kind of like in the tabular methods from part 1 of the book, the exact solution is a fixed point of the Bellman operator. In the approximation space, the TD fixed point is like a fixed point of this projected Bellman operator. So even though like we are minimizing this error, but we're not just minimizing it, we're actually like bringing it to 0 when we find the correct approximation solution. And it's something that we can always compute, even like no matter what the problem is, because we can do it for continuing problems because we have the bootstrapping. But there's a lot of sort of algebraic details in how this algorithm is derived. But visually, what the error that's actually being minimized is this. If I move this around, like wherever this Bellman point ends up being, you can always project it down into the plane here. And then at some point, it's guaranteed, at least for linear approximation, that there is some point in the approximation space where this projected Bellman error is exactly 0. And that's the point that we're trying to find with this algorithm. Now, they end up writing it down in a few different ways. The final update rule that is derived is this one, and they sort of separate the approximation into 2 pieces. The reason why there's 2 pieces here is this piece is sort of accounting for the visited states. Like you notice that this doesn't depend on, I mean, it depends on the parameters with the delta term here, but primarily this is dealing with some approximation related to the feature vectors that are visited. And then it appears down here, but there's sort of 2 update steps. There's one step that updates this vector. And they say, again, like another thing this vector is doing is it's something which is trying to predict the TD error or the corrected TD error from the feature vectors. And then here we have, the TD error. Now, what I'm not exactly sure about is in the on policy case, I thought that this algorithm should be equivalent to the semi-gradient TD update, because we already know that the semi-gradient TD0, like that's Yeah, I mean, it was introduced in this chapter, and it's what we were using in these on policy methods. But right, if we use this and we compute the gradient, ignoring the fact that this depends on W, we already know that this should converge to the TD fixed point. And the whole point of this algorithm is to converge to the TD fixed point, like even in the off policy case. But if you look at all the math, I was having trouble seeing exactly like, right, this has this importance sampling ratio in it. And obviously in the on policy case, this importance sampling ratio is always 1. But there's these other relationships with the expected value that I'm not sure if it, like you can take individual examples and try to show that this projected Bellman error update is the same as the semi-gradient update, but I'm not sure how to show it's equivalent in general. And it might not actually be equivalent because the learning rate might, like this might be like effectively like semi-gradient TD0, but with a learning rate which sort of changes or depends somewhat on what state you're in. I'm not sure exactly, but you know, it's already been derived in the book anyway. You can implement this like I've done here for, you know, so here, like this function is going to take, you know, some target and behavior policy, which, you know, now we're free to make them different, and some problem. And what it does is it applies these two updates. So it keeps track of both, like it keeps track of some vector v, and then it also keeps track of the weight vector. And of course, the way this was derived, this is all assuming linear approximation, right? So this gradient TD method, yeah, I believe, yeah. So this entire method is assuming linear approximation. So unlike the previous like semi-gradient method where we could, if we want, apply it to some nonlinear function approximation case, here, the only thing that has to be defined for this algorithm is something that updates the state representation. Because if you look down at like all these gradient terms, like we need the state representation, we need to use that, and that's basically the only thing that we need to implement this algorithm. We need to just have a way of mapping a state to the state representation. And then all these update steps in here do that. Now, the claim here is, remember, we had the case of Baird's counterexample and how if we tried to visit the states in a way that didn't match the target policy, then we got diverging weights. That's what was shown up here. So we had this behavior policy that visited all the states equally, and the target policy only, in general, like only spends time in one state. And then if we try to apply that with off policy methods, we get all the weights end up diverging. Of course, in the on policy case, it's fine. So if we revisit this example now using this algorithm, which is called, I guess, TD0 with gradient correction, or, you know, just GTD, then they have a diagram in here that this is showing a couple of the weights or combinations of weights. But you can see that none of the weights are diverging in value. The value error is also dropping. The point of this algorithm is to take the projected Bellman error to 0, which we can see also happening here. This is just showing here, I'm just applying this version of the algorithm to Baird's counterexample. There's also, I did some, if you look at the problem analytically, the value error, right? The target policy is the one where all the time is spent in state 7, right? Which is this state. So the target policy takes the solid action. It only spends time in this state. Now, because of that, all these metrics, like the Bellman error, the value error, the projected Bellman error, they only depend on the value here. Like all the other values are irrelevant. So we can look at this value. It was represented by W7 plus 2W8. We know the true values are 0 for all of these because all the rewards are 0. So, right, we know that there's sort of an infinite family of valid exact solutions to this, right? We just need this state value to be 0. And that happens when W7 is minus 2W8. Now, the mean squared Bellman error, yeah, I mean, this again is like a tabular problem. So we end up getting the same solution. If we look at the projected Bellman error, the projection operator, again here, because we actually have more parameters than states here, we can just end up choosing, like leaving the parameters unchanged. We don't have to project anything here. So fine, like we already know that if we apply the projected Bellman error in this problem, it won't diverge. We should get the exact solution, which all matches. But if you actually compute the projected Bellman error on this problem, like not the value that minimizes it, but just given values for W7 and W8, like what is the projected Bellman error? It actually is the same as the value error, as the mean squared Bellman error, right? Because the projection is not necessary in this case. If you compare it to the value error, you can see that it's actually just the value error times this factor 1 minus gamma squared. Now, if gamma is close to 1, like 0.99 or something, this is a tiny value, right? So whatever the value error is, the predicted Bellman error is much smaller than that. So if you look at this, we can see like all the weights are converging fine. Now this pink line, just like we have down here, you can see like this green line here and this pink line. It's pretty far, sorry, this pink line is pretty far from 0, right? Like at the optimal solution, the value error and the predicted Bellman error are both 0. But I already showed that if gamma is close to 1, it makes the predicted Bellman error like very small, which makes this converge very slowly. So that's one of the problems with this algorithm, is like you can have situations like this where even though when it converges, these will both be 0, the predicted Bellman error here is tiny, like it's 0.02, or this is the square root of it. If you square it, it's even smaller. So the convergence is already very slow for this, whereas this is quite far from 0. And depending on the, so if you change gamma here, like if I were to set gamma to a much smaller value, like 0.1, and redraw this, then the convergence will be much faster. So here, wait, where is, yeah, so I believe, yeah, so we have this pink line and the orange line here. And now you can see these now are both going to 0. I mean, this is still, the learning rate is probably too small for this. But you can see that because I've made the gamma closer, like as gamma approaches 0, the value error and the projected Bellman error will, oh, okay, that's clearly way too big, will match in value, and you won't have this slow convergence. But the point is, like, the origin of this slow convergence is because of the discount rate here being close to 1. And, but also, so this isn't like an algorithm which is spelled out in the book, but this is sort of how you could use this projected Bellman minimization for a control problem. So here, instead of doing the policy estimation, I'm doing control where I'm going to try to find the optimal policy using policy iteration, where I'm doing kind of like what we did with semi-gradient SARSA or Q-learning, where I'm going to have the, in this case, either the state or the state action value approximations. And then I'm going to use policy improvement on the approximation to try to compute the greedy policy with respect to the current value function. And here, I don't have a target or behavior policy. What I'm going to do is start out with a random policy like we usually do for this. And then this is sort of like doing Q-learning, where, remember when we did Q-learning, we have the target policy, which is the optimal policy. And the behavior policy is going to be the epsilon greedy policy. But all of the bootstrap approximations we're going to do based on the greedy policy. So that's what makes it an off policy method, which didn't have any problems converging in the tabular case. Now, there's this idea that it might have a problem converging if we do semi-gradient TD0 because of the examples in this chapter. Now, this instead is using this set of updates to try to compute the gradient update, where, the delta term is actually going to use the delta from the target policy, which is optimal, whereas the actual samples, like the trajectory that we sample, is going to follow the behavior policy, which is epsilon greedy. So, you can look more in the details of how this algorithm works. There's actually there's two versions of it. There's one version that computes state action values, which normally is what you need to do. There's also a version here which computes state values, but it does require that the MDP have the full distribution information for the transition. Something I mentioned before, but if you actually have the full distribution of the transition, then you can derive the state action values from the state values. You don't need to, store a separate estimate for each one. But I did try applying this because there was this problem, this exercise, where it was saying, if you apply Q-learning to Baird's counterexample, show that the weights diverge. And I saw that actually over time they converge, but the initial training process, like if you look at the first 4,000 steps, you can see here that the state values are diverging, like they're growing. Like we know the true state value should be 0, and they are not going to 0 initially. They are growing. This is trying to apply the same like Q-learning now with the, corrected gradient algorithm. And you can see here, like this diagram, this is showing just the estimation problem, not the control problem. This is doing it with a control problem with Q-learning, both versions of it. I think, yeah, this is the version that uses the dynamic programming version, which is this one. And you can see that unlike the previous one, actually these weights don't diverge even at the beginning. I mean, there's some stochastic noise, but these are all the parameters and state values here. You can see like they're not actually converging very quickly to 0, which is the problem we had here still. But they are not, the weights are not diverging in this case. So it seems like you can actually implement this, even a control version of this, with these updates. And I don't know if it's always better to do this version of like Q-learning with approximation compared to just doing the method before. I also, in chapter 10, there was the mountain car example, and I had applied this same like dynamic programming Q-learning to mountain car, where again, like there's some value of epsilon here, and just like with other Q-learning, right, you're following the policy with epsilon, you're trying to compute the optimal values where epsilon is 0, what's off policy. Now, in the mountain car problem, there wasn't an issue using this. In fact, even setting epsilon to a very large value here, like here, oh yeah, I think here actually, yeah, I'm setting epsilon to 0.9 here, which is very large. And you can see it's still not diverging. It's able to converge. This is showing the same thing, but using this TDC learning with Q-learning. And like both algorithms appear to work. Like I haven't yet found, like it's unclear if there's any examples where this method of Q-learning with approximation actually diverges. I mean, even with a very high epsilon, but that doesn't mean that there's no reason to do this, because it's possible that if you apply this version of it, that it converges more robustly. And here I'm just showing like individual examples. Yeah, in this case, probably the learning rate has to be made smaller again. But like to really test this and see if there's any point to using like this algorithm for control, you would have to see if it just more easily finds a good solution across a range of parameters. You'd have to do some kind of parameter study. I mean, one thing that is somewhat encouraging is the fact that here there's no initial divergence of the weights, which is good. Yeah, so that's something I haven't added that to this yet. I might add it and like show it briefly at some point in the future. But I think like one way to see if there's any use to this is to like look at this mountain car problem, for example, and see if this version compared to the the old method from chapter 10, if it's sort of more robust under different parameters. However, this algorithm has 2 parameters because there is a learning rate for this quantity, and there's also the learning rate alpha. So you do have the problem of selecting 2 parameters, but if the algorithm is more robust across a wide range of parameters, it might still be easier to optimize. I don't know, but that's something, I guess I'll make a note here of wanting to do that. But yeah, because I think other than doing that, I mean, I guess this is already one demonstration that it might be better than just doing the Q-learning, the semi-gradient Q-learning, where you don't have divergence. But this is sort of an unrealistic example to begin with. So I don't know how relevant this is. This is a more realistic example. And at least like, so just testing it out initially, it does seem like this is finding pretty good solutions a little more easily than this method, but I can't say for sure. I don't think, I won't really talk. I think this method, this is mentioned, but these converge even worse than the TDC method here. So I won't talk about it. Yeah, so I think that's all I wanted to talk about in chapter 11. Again, if you want to see that this sort of TD control algorithm isn't mentioned in the book. These parameter updates are only for approximation. But if you want to read this in the notes on GitHub, you can see how I did it. but it's just sort of a version of Q-learning, but using these updates. And it uses this sort of epsilon greedy policy on every step. Okay, are there any remaining questions for chapter 11? I'm sorry. Yeah, if not, I think next time we'll just move on to chapter 12, which is quite a bit different. And hopefully, yeah, anything that was unanswered will be a little more clear reading the notes.